Well, we're Team 17, and this is our final presentation for Dr. Kosaraju's Mechanical Engineering Design class for Semester 1.
So a quick overview of what we're going to be speaking about today. We're going to talk about our initial project ideas. So it's a couple ideas we have of what we're going to do for a project for this class. Then we're going to go and talk about the Kayak Pak, which is the project we ultimately went with. And then we're going to speak a bit about the objectives and constraints of this project. So we're also going to go over the quality function deployment and the house of quality. And then we're going to talk about our concept combinations. So each team member came up with a couple of concepts, drew them out, sketched them out, and we're going to speak about that. And then we're going to go into our design criteria. And then that will lead us directly into the analytical hierarchy process. And then after that, we'll talk about our preliminary design, and the design we went with. And then we'll speak about the engineering calculations and the results those gave. And then in conclusion, we'll finish off with the critical element demonstration.
So these are our initial project ideas. Our first idea was for a collapsible kayak, just a kayak that you could easily transportable, and you can collapse inside a backpack. You can use it whenever and wherever you so please. Another idea we had was a wrinkle-free shirt magnet. This would be a device you can put by like the buttons on a button-up shirt or a polo to make sure that this area here doesn't get all wrinkled up. A third idea was an automated outfielding machine. A user would input a specified height, speed, and location, and this machine would shoot a baseball, softball, what have you, at that location. We ultimately went with the collapsible kayak idea, and we named our product the Kayak Pak.
So, there is a need for a better designed kayak. Kayaks nowadays, they are rigid, one piece, they take up a lot of room, so they're hard to store and they're not easily transported. That can cause an issue for those who are hoping to get into the sport of kayaking, and also poses an issue for relief efforts. As we see here, the initial relief effort is done by the people from the area with their own boats, inner tubes, whatever they have. So, a collapsible kayak that takes up a small footprint when it's collapsed and is also easily transported can be easily deployed in areas for relief efforts and also can work well for the beginning outdoorsman.
To satisfy these needs, we came up with our ultimate goal statement to design a lightweight, collapsible, and easy to carry kayak with an emphasis on the collapsibility.
So one major objective we have is it needs to be inexpensive. This is for the beginning outdoorsman and also for relief efforts. And then it also needs to be lightweight, helps out with the ease of transportability. And then it also needs to collapse into a small size to carry. That way the outdoorsman, or for relief efforts, they can pack it in and out of where they're going easily. The kayak must float. It also, so the pack design for the kayak has the dimensions of 36 inches high and 10 inches by 10 inches. So the collapsed kayak must be able to fit into the bag. And then the kayak needs to support a rider up to 220 pounds.
So with those objectives and constraints in mind, we came up with customer requirements that the customer would want for a collapsible kayak, as well as engineering requirements for us to keep in mind throughout the design process. Some main customer requirements would be that it's aesthetically pleasing, durable, so they're buying something that's going to last them multiple years, lightweight, inexpensive. Some main engineering requirements are the buoyancy and the material selection. Material selection is going to affect the cost and the weight, which will also affect the buoyancy. And if we have a high cost, then we're not going to be able to maintain the inexpensiveness for customers, which you can see when compared to our two main competitors, that neither one of them are inexpensive. And we meet our customer requirements way better than either of those two competitors. Using the engineering requirements, we developed a relationship between all of them in the house of quality. You can see they mainly have positive relationships to one another. The only negative one is between buoyancy and weight, which ultimately, if the weight is high on the kayak, your buoyancy factor of safety is going to be low, and vice versa.
So in order to make sure that our product would do well, we had to do a state-of-the-art research on the open market. Right now, our best competitor is Oru Kayak, as shown here. They use polypropylene plastic rigid sheets in order to achieve collapsibility. They fold them up using an origami technique. It is lightweight, it's about 24 pounds, but that is a constraint that we are trying to beat with our product. Some of the downfalls of it is very expensive, and so it's hard for the consumer to easily purchase. And as you can see in its collapsed state, it is at a very large size.
So with our main competitor in mind and our objectives and constraints, each team member came up with 2 concepts, and out of those 12 concepts, we then picked the top 10 to move forward with in our design and decision-making process. Concept 1 is the pack itself, which meets our constraints of being 3 feet tall and 10 by 10. The main pocket has a drawstring opening for all the main frame components, a lower pocket for any odd-shaped frame component, a side pocket which is for the user and their belongings, as well as straps to roll the shell up and attach it. Directly related to concept 1 is concept 2 with a pre-sewn pocket of a shell that can easily roll up and be strapped to the bag. And then here's the frame for this concept, which has 4 hull supports, 3 vertical supports on both sides, a wide stern, and a narrow bow. The main design here is that you can assemble the frame, put it inside your shell pocket, and then there's extension joints in the center so you can extend the frame and it will create the shell to tighten on itself and become a waterproof, usable kayak.
For our third concept, I started with a rigid frame, as you can see in the middle. It's an aluminum cube, 2 foot by 2 foot by 2 foot. On each side of the kayak, there are metal rings, C-rings on each side, connected with cable. Ideally, these would be retracted into the rigid frame, set inside the shell, which is preformed and sewn, and then extended out to make the kayak possible. For our fourth concept, it's a little bit similar, again with a rigid frame in the middle where the rider will be sitting. Again, aluminum rigid cube, 2 by 2 by 2 foot. On each side, we're going to have telescoping rods. They're going to telescope out once the rigid frame is set inside the shell, and then fastened to the shell material as well.
Our fifth concept consists of wooden ribs along the length of the hull and 2 wooden end caps on either end. Telescopic rods extend from the middle through the ribs and end in the end caps. And the shell material is hooked to one side and then wrapped around the hull and hooked to the other side. Our sixth concept is similar in that it involves wooden ribs along the length of the hull and wooden end caps. However, instead of telescopic rods, there are rigid beams that hold the ribs in place, and the shell is made of metal sheets that are sandwiched between the wooden ribs and the rigid beams.
So for concept 7, the frame itself, much like tent poles, has 2 poles, there's a coupler in the middle, and then there's elastic in the poles so they stay together. That way they're easily foldable and unfolded. And then the shell would be pre-sewn into the shape shown, and then it would attach to the top rail via butt snaps. And then for concept 8, the poles remain permanently attached to the shell itself, with the exception of the 3 top poles. The top poles are extendable, and then once you remove them, this looking from the front, it will clamshell together and then accordion up lengthwise.
So concepts number 9 and 10 both deal with different ways to bind the outer pieces of the kayak shell together. For concept number 9, here you can see one of the outside vertical pieces. This piece has a screw extruding inward out from the piece, along with 2 horizontal guides that run along the top and bottom. This screw and these guides then meet up with the centerpiece, which has a large slot that allows the kayak to be adjustable to a user. Both sides of this slot are coated with a rubberized surface to prevent sliding. Then a hand-screwed bolt is attached to the screw to bind both of the pieces together. This concept 10 also deals with a similar concept. This horizontal piece has 2 vertical guides running that allow a piece with a bracket on the top to be slotted over it. Both this horizontal piece and the vertical piece have pinholes in them that allow a pin to be inserted between the 2, binding them together as well.
So with 10 concepts, we needed to narrow down our options in order to develop a final design to carry forward with and create a preliminary design and perform our engineering calculations on. So we developed these 8 criteria to rank each of our concepts relative to one another, which you can see are closely related to our objectives that we set forth at the beginning of the semester and the beginning of this presentation. Each criteria is more or less important than one another, so we had to our first step of the analytical hierarchy process was to normalize our preferences and develop the weight for each one. We are not going to be ranking concept 1, which was the pack itself, or concept 9 and 10, which are joint connections, which we could apply to any of the designs we chose. Using this numerical scale, we were able to score each concept based on their design criteria and based on what the designer themselves estimate to be the where they're going to fall on this scale. For preferences, in order to get the weights of our design criteria, we use this table here. Extremely preferred is a 9, equally preferred is 1, which you can see comes into play here where cost is equally preferred to cost, and weight is an 8 compared to cost, which means weight is much more important, much more preferred over cost. With that table, we then normalized our preferences and developed an average weight, which you can see here is our relative weight for each criteria and how important it is. So with that, we found out weight is the most important, with being worth 32.6% of our design, volume being second at 22.7.
So using these weights for each individual concept, each concept was scored. So concept 2, our ultimate highest scoring concept, ended with a score of 7.58. Concept 3 ended with a score of 7.4. Concept 4 ended with a score of 5.09. Concept 5, our second highest score, ended with a score of 6.52. Concept 6 ended with a score of 4.18. Concept 7 with a score of 3.69. And concept 8 with a score of 3.66. So as I mentioned earlier, our highest 2 rated concepts, concept 2 and concept number 5, ended up being our highest, and were then compared farther.
So now we've narrowed our options of what design to carry forward with for the rest of the semester down from 7 to 2 concepts. So then James and myself drew up more detailed drawings to present to the team and discuss it as a team, and then we voted as a team for which of these 2 concepts we wanted to carry forward and create a preliminary design for and ultimately build in the end. Here are the more detailed drawings for concept 2. You can see this is the bottom side rails with an ultimate length of 12 feet and a width of 20 at its widest portion. And then you can see the top, which has a 2-inch offset from the bottom, 2 inches in length each way and in width each way, which you can also see here, as well as the overall height of the kayak being 10 inches. Here you can see the hull supports for and where they are located along the length of the kayak, a depth of 1 inch in the center and a depth of ½ an inch on the end caps. That's to ensure a shallow profile and for fluid flow. And here you can see the location of the vertical supports for the frame.
Here's a more detailed drawing of concept 5. Again, it involves wooden ribs and wooden end caps. The telescopic rods are extended from the middle through the ribs and into the end cap. What you can see here, the holes in the ribs are displayed on a frontal view there. And there's a concept of what the telescopic rods would look like. It ended up being 8 feet by 15 in height. And overall, in the end, we went with concept 2.
So here we can see our initial model of concept number 2, modeled in ANSYS using finite element software. So this model consists of 6061 T6 aluminum tubing as its primary material. So in order to generate this model, we had to make a number of assumptions, the first of which being that these long straight pieces, which would regularly be curved on our actual model, could effectively be modeled as straight, because this wouldn't affect the stress distribution through them at all. The second assumption was that in order to simplify our joint connections, we would be able to model this effectively as a truss, so that we wouldn't have to get into nitty-gritties with all of our individual connections between pieces. So using this model, we had to do 4 basic tests to determine that it would be effective. The first, a simple buoyancy test using the load of a rider and the force from the kayak to determine it with load. The second, a structural test determining the pieces themselves wouldn't break under weight. The third, a collision analysis ensuring that when the kayak encountered an obstacle, it wouldn't break. And the fourth, to determine the coefficient of drag on the kayak itself.
So as Randy stated at the beginning, one of the most important constraints for a kayak is that it floats. So using an average between the top and bottom dimensions of this kayak and straight line approximations, we were able to come up with a rough area for the overall kayak, which we then multiplied by the height to find the volume of the kayak. With the overall, with the overall volume, we only want 50% to submerge it. Worst case scenario, we want at least 5% of the side of our kayak staying above the water level. So with that, we multiplied that amount of volume, the submerged portion, by the density of water, and found the buoyancy force to be 406. And since in our constraints we set forth that we have a total of a max rider of 220 pounds, we have plenty of room to work with for the material, but lightweight is still a main objective for this kayak. So with our rough estimated dimensions, we calculated the weight of the frame and the weight of the kayak shell, which will be billboard material. And knowing we're using 6061 T6 aluminum, the overall frame is going to weigh around 10 pounds, and the kayak shell is going to weigh somewhere between 3 to 5. So adding that 15 pounds to a max rider of 220, we were able to find a buoyancy factor of safety of 1.73.
Just a couple more calculations. If we use the cross section of our kayak here, we determine the angle for tilt for the operator, the degree of safety. So we determined through the geometry that it would be about 55 degrees that the kayak can handle without capsizing.
So then here we can see our structural analysis of the kayak. So here we again made two primary assumptions in regards to how we model this force. The first being that in an absolute worst case scenario, both ends of the kayak at the front and the back would be elevated off the ground, which allowed us to model them as fixed structural supports. And the second being that a rider over a normal maximum weight capacity would be at the center, which was modeled in 4 downward facing forces of 75 pounds each, resulting in an effective 300-pound load. So this structural analysis ultimately gave us a maximum stress of about 5,400 psi and a factor of safety of around 7.4. Then, with our collision analysis, we made another set of assumptions, the first being that the same 300-pound load is in play, the second being that the kayak is traveling at about 5 feet per second, giving us a maximum force of around 1,500 foot-pounds. This force was then used in order to calculate how much stress the kayak would take in an elastic collision, ultimately giving us, for our direct stress, a factor of safety of around 49.3, and for maximum combined stress, a factor of safety of around 11.5.
And moving on from our collision analysis, we went on to a fluent analysis to determine our coefficient of drag. This figure here shows the wetted profile of the kayak, which is approximately 50% of the total kayak shape. Subjected to a channel of water from inlet to outlet there, the water moves at 3 knots around the shape of the profile there. We ran the solver for 200 iterations and it converged to an approximate coefficient of drag of 0.75. This figure shows the vector profile of the channel of water and vortices forming on the back side, and this figure shows the inlet and outlet mass flow rates are similar. However, we thought that our coefficient of drag was kind of high, so we did further hand calculations to confirm our suspicions.
So for the hand calculations, we did 2 different calculations. The first, we took the bottom area of the kayak. We approximated flow across a flat plate. With that calculation, the flow turned out to be laminar. We got a coefficient of drag of 0.003. But through ANSYS, we see the vortices and the flow would be turbulent, not laminar. So we did another calculation with turbulent flow. So for this, we took the wetted frontal area of the kayak itself, and then did the hand calculation with that, but that also gave us a coefficient of drag of 0.003.
So in conclusion with our calculations and analysis, we came up with a factor of safety for buoyancy, our structural material, as well as the collision. And all these were high enough that we would go ahead and accept our preliminary design with our kayak. We also calculated again the degrees of tilt and then the coefficient of drag as well. So for our critical element, we were discussing with Professor Kosaraju, and he recommended we shape the frame of our kayak. As you can see here from the top, we were able to bend the aluminum tubing to make the lower part of the frame. This would be the front part, the middle part, and the lower part as seen above. In between these tubings where the tubes will actually meet, we're actually going to have a solid piece of aluminum that's going to slide in between or inside of each tube snugly. And with that installed, we'll be able to handle the stresses that the kayak will endure. But in conclusion, next semester, we're going to go ahead and continue to build on this frame. We actually need to make another shape just like this. It'll be a little bit smaller with vertical supports and then the lower hull supports as well.
That was pretty close to 20.